Greetings, physicists. This video will be about solving problems involving electric potential and electric potential energy. Okay, so we've got a particle who's going to move from a point where there's a high electric potential to a point where there's a low electric potential, and he has a positive charge. And we're going to ask, how much does the electric potential change? And that by itself is a fairly easy question, right? If you go from 300 and you move to minus 200, you have lost potential. In fact, you've gotten a net change of 500, negative change. So how much does it change? It changes by minus 500 volts. That's the potential change. There, okay? So that should be pretty straightforward. Then we go, by how much does the electric potential energy change? And now we have to do an energy calculation. So potential energy for a charged particle, U, is equal to Q delta V. So in this case, we know the charge, it's a 15 nanocoulomb charge, and we know the change in voltage. So I'm just going to plug those in. The Q is 15 times 10 to the minus 9 coulombs. Okay. And the voltage change was this right here, which was negative 500 volts, or joules per coulomb. And so coulombs will cancel. And I'm going to write this as 5.00 times 10 squared. And you'll see that that's just those two tens, and those minus 9 tens go to minus 7 left over. And then I have 5 times 15, which is just 75, or negative 75 in this case. Come on. There we go. So I'm going to have negative 75 times 10 to the minus 7, and then if I put the decimal there, it becomes 10 to the minus 6, so negative 7.5, 10 to the minus 6 joules. And that negative just means I lost that many joules. By going from high potential to low potential, this object is losing potential energy, or converting it to kinetic, I suppose. Okay, how would your answers change if the particle had a minus 15 Newton nanocoulomb charge? Well, if it has a minus 15 nanocoulomb charge, then going from high potential to low potential is actually an increase in potential energy, because essentially when we think of potential, here's a positive, right? This is a field. Potentials are always probed with positive test charges. So a positive test charge moving against the field is going to a high potential, and a positive test charge moving with the field is going to a lower potential. And going away from the charge, it loses potential energy. It gains potential energy going towards it. But it's the exact opposite for a negative particle. A negative particle going against the field is going the direction it's being pulled. It's losing potential. If it goes with the field, it's gaining potential. And you want to think about the direction the force applies. Okay? The force on this positive particle is out. That's F. Think about gravity. If you let gravity push you, you go with the field. You go downwards. But you lose potential energy. You gain kinetic. So when this positive particle goes with the field and gets pushed that way, it's losing potential. If it goes this way, it's going up against gravity. Right? Gravity is if you were to go up in the air and away from the direction the force of gravity pushes you, you gain potential energy. So think about, where does this negative particle get pushed by this field? It gets pushed this way, towards the field. That's the force. So in order to gain energy, it can't go with the force. It has to go away from the force, to gain potential energy, I should say. So how does my answer change if the particle is negative? It gains that energy for going the same direction the positive particle went. Okay? So that's the way those work. All right. We have a positive particle that's going to move from point 1 to point 2. As it does, what happens to its potential energy? So I need to mark this as a positive particle moving that direction. What is that positive particle doing? Well, these things are producing a field like this, and that field is going to push that positive particle. So it's going with the field, right? Not against gravity, it's going with gravity. When we go with gravity, we tend to lose potential energy. So let's see what's happening with these negatives. Well, negative, the field points towards a negative particle. So those arrows, look which those arrows are pointing this way towards that. So this positive particle going this way is also going with the field on the right side. So it's still losing energy, potential energy, relative to those charges as well. So at every point along the path from here to here, it is going with the field, which means it's going to decrease its potential energy. It's going to speed up. And when you gain kinetic, you have to lose potential. Okay? Last one. Last one? Yes, last one. Okay. Another proton moving through an electric potential. And now we have a speed thing. Okay, good. So now we're going to talk about kinetic energy. And we have potential at one point, and we have potential at the next point. So this is a conservation of energy problem. We can see that it's losing potential energy. It's going from a high potential to a low potential, and it's a positive particle. So positive particles that go from high to low are losing potential energy. And we can see that there's going to be some speed energy as well. Yeah. So let's think about this. Here's the proton at 1500 volts. Proton, there we go. It travels over here, and it ends up at minus 500 volts. And it started with, its speed was this at the 1500 volts. So I'm going to mark that here. 2.5 times 10 to the 5th meter per second. So it actually starts with both electric potential energy and kinetic energy. What's it going to end with? Well, it has some amount of electric potential energy, although now it's negative, and it has presumably some speed, so it should have some kinetic energy as well. So we're just going to set up a conservation of energy equation. All the energy it starts with has to equal all the energy it ends with. So at the top, the potential energy, U, which in this case is Q times V, plus the kinetic energy, which is half mv initial squared, should be equal to, at the end, QV plus the kinetic energy at the end, which is half mv final squared. And I'm looking for this V. Now, I haven't drawn this great, but there should be capital V's and lowercase v's, but we'll kind of deal with that. So I'm going to subtract this first. I'm going to get the Q, I guess this is capital V initial, plus half m V initial squared minus Q, and that's V final. And then all of that equal to half m times the V that we're looking for. So if I multiply by 2 and divide by m and then square root it, I will get V. Okay. So plugging in everything I know, and I got to remember my proton business. I can actually factor the Q out of these, and that'll be a little easier, I think. Do a big square root here. So if I factor the Q out, that's going to be 2 times, and here I'm going to have that'll be Q times V minus V final, and it's going to be, let's see, that should be a Q, not a G. Herp. There you go. Plus half m the initial squared over m. Okay, and I can distribute the 2, because that's going to cancel this thing here, and then just put the 2 in front of the q there. So if I'm cleaning this up, which I probably should before I plug numbers in, I'm going to get square root of 2q vi minus v final plus mvi squared over m. Okay. Note that these values, sorry, the v's, the voltages were given to me. The initial velocity was given to me. I need to look up the mass and charge of a proton. We had looked up the proton before. So we know that that's going to be 2 times 1.6 times 10 to the minus 19 coulombs. V final minus V initial is 15 minus 500, or 2,000, which I'm going to write as a power of 10, because I know in these problems powers of 10 happen a lot, plus the mass of a proton. Or let's ask Siri. 1.6 times 10 to the minus 27. 1.6 times 10 to the minus 27 kilograms. And the initial velocity squared, I'm totally running out of space here. Let's see if I can't squeeze it in. The initial velocity squared was 2.5 times 10 to the 5th, I think. There. Over the mass again, which is 1.67. Forgot the 7 up there. Times 10 to the minus 27. All right. The trickiness in here is that there's a plus. That's going to be a tough one. And you'll see why, because there's a lot of different powers of 10. You can only add powers of 10 if they're the same. But let's try and resolve the top. 2 times 1.6 is 3.2 times 10 to the minus 19 times this 2, I suppose. So I'm actually going to make that 6.84. So that first term is a 6.4. I have minus 19 tens plus 3. I'm going to have minus 16 tens here, plus 2.5 times 1.67. I'll need the calculator to do that for me. And that's going to tell me 4.175. I have minus 27 plus 5, so that's times 10 to the minus 22. So I need to, well, over this, 1.67 times 10 to the minus 27. So what you need to notice about the top is that their powers of 10 are very, very different, and we're adding them. So let's look how much different they are. Well, this is minus 22, this is minus 16. So essentially this is 6 powers of 10 different in a 2 sig fig problem. 2 sig fig problem. So I can add this and it's not going to make any difference. And to prove to you, let's turn this into a 10 to the 16th. What would it look like if it was a 10 to the minus 16 so that I could add this to this? I have to move that decimal 6 times. 1 and then 5 zeros. So I'm going to have 1, 2, 3, 4, 5, and then the 4175. If I add that to this guy, I'm going to get 6.4 still, and then 0, 0, 3, 4. Well, so that's, yeah, so there'd be 4 zeros, and then the 4, 1. See how that doesn't make any difference? It's still 6.4, all right? So I don't really care. This term is eliminated by sig figs. So what I'm really doing at the very end here is 6.4, 10 to the minus 16th, over 1.67, 10 to the minus 27th. So this term here was the velocity, and so the kinetic energy that that proton had to start with was completely negligible when we compare it to the electric potential. All right, I have minus 27 on bottom. If I pop that up the top, that's positive 27. Minus 16 will be left with 11. Yes, yes, I just had to make sure I believed that. Sorry. Okay, and let's do the 6.4 over 1.67. 6.4, yeah, divided by 1.67, and I'm getting 3.8. So 3.8 times 10 to the 11th joules. Oh, no, no, no. Haha. I didn't square root this. I have to square root this. So your tip for there's so much in this problem. You're gonna like this problem later because it has just about everything that could be messed up in a problem. If you want, if you type this into your calculator, and your calculator is one of those where you can just hit the square root button, you can go ahead and take the square root of that as is. Again, I don't like putting tens in my calculator. I prefer to do them outside. But this is one of those situations where it's tricky because it's hard to take the square root of an odd power of 10. It's easy to take the square root of an even power of 10. So what I'm going to do is move this decimal over to make it 38. So I'm going to do the square root of 38 times 10 to the 10th, because then I can take square root of these by themselves. So the square root of 10 to the 10th is just 10 to the 5th. And then I'm taking the square root of 38. All right, 38, and whoops, delete. I need square root of 38. And that's 6.2. So 6.2 times 10 to the 5th. And I just remember this was supposed to be a velocity. So this is a meters per second. Now let's check to make sure that that answer makes sense. And I'm going to tell you what I'm looking for. I'm looking for a number that's bigger, right? Because this object went from a high potential to a low potential, so it lost potential energy. It should gain kinetic. But I'm also looking for a number that's less than the speed of light. One of your indicators here is that 10 to the 5th is a lot. It's fast. So you want to make sure that you don't get an answer to this problem that's too fast. And too fast would be breaking the speed of light, which is not physically possible. And most tests that are written by professionals, aka not me, will have pre-cooked their answers so you don't get impossible stuff like faster than the speed of light. Well, the speed of light is at 10 to the 8th meters per second, so we are less than that. And our original velocity was 2 times 10 to the 5th, and we got up to 6.2 times 10 to the 5th. So we basically tripled our velocity. Maybe 2.5 times our velocity. Triple would be 7.5. Okay, so this does make sense. We gained a bit of velocity there. Okay, hopefully this video was helpful in you and your solving your electric potential problems.